Okay, we're going to do one of the last topic related to beams, but we'll do it twice. We'll do 2 days of it. This is the first part of beam deflection. So we've talked about beams as part of frames in machines. We talked about beams, flexural stress in the beams. We talked about the shear and bending moment diagram of a beam. And now we're going to talk about the deflection of beams. So are they going to bend, and how much are they going to bend is basically what we're going to talk about today. Like I said, we'll do this in 2 parts. This will be the first part, more of the theoretical side of things, and we probably will end today with some of the chart type methods, kind of like we did with centroids and moments of inertia, where we looked at it from a theoretical kind of view, at least for centroids, and then we said that a lot of this has already been done, and there are these charts that you can use. There's similar type things for beams, and a similar way to take several 8 or so simple cases and combine them together, superimpose them on one another to create more complex situations. So why don't we start with this beam deflection. And let's just start with talking about what it is we're even talking about, so that we make sure that we're on the right track. Let's use a cantilever beam to start with. So here will be our little beam. Let's make it a T-beam, so it'll have a little line across there or something. And then we'll mount it to the wall back here, and we'll say that this is, remember, when it's fixed in one place, whether it's like a signpost stuck in the ground, or whether it's like we've drawn here, some kind of beam attached to a wall or whatever. It doesn't really matter how it's attached, if it's welded to it or bolted to it or embedded in it. We're calling these cantilever beams. I'm just going to put a single point load on this one out at the end. Oh, wow, not like that though. Erase the R. There we go. Single point load. It doesn't really matter how much it is. We'll just call it F. So assuming that we push hard enough on this cantilever beam, then it will bend and it'll deflect. And with this point load, then it'll probably do something like, let's just take a midline. No, let's do the top. Now I'm going to exaggerate it. Something like that. And this is our delta, or might be y, if this is a movement in the y direction. And we could even have an equation for this curve that I've kind of drawn with the green dotted line. It could be an equation that models that curve. In fact, this would be called the equation of the elastic curve. And we're specifying elastic because if I bend this beam too far and it goes into that plastic region where things begin to deform and they never go back to the original shape, that's not where we're talking about. We're elastic curves, so this is more like a diving board where you bend it down and then it pops right back up once you release the weight from it. So it's still in the elastic region. Remember, let's just real quick draw our ductile stress strain plot just to do it. So remember, there's a straight linear region, that's the elastic region, and then there's a curved region where it's plastic deformation. So we have the elastic region down here and the plastic region up here, and they kind of end wherever that elastic region is no longer linear. This is strain and stress. So this would be a very ductile type material. Normally this elastic region, the linear region, is much more vertical. I've just kind of exaggerated it so that we could see it versus it being a vertical line almost. So we're operating down in this region here with our beams. If we get into that plastic region, then we have gone in some place where this beam does not need to operate, and this equation would not model it correctly anymore anyway. It's going to have some kind of permanent deformation. All right. So equation of the elastic curve, that's a thing that we would be very interested in. And so that's what we're going to look at. How do you develop this equation of the elastic curve? So we're going to do that today. We're going to basically develop an equation of the elastic curve. And lost my cursor. There it is. Let's do that by, let's draw a simply supported beam. I think that'll work better for what we want to do now. So simply supported beam, it'll be supported with a pin and a roller. Doesn't really matter where, except we're going to put them at the ends. And we'll put a load on this enough that it would also bend. So let's just put a point load, and let's say that this guy would bend, something like this. And we want to figure out the equation of that curve. So let's take a tiny section of this beam, so maybe our little section right in the middle, and really exaggerate it and blow it up a lot bigger. And again, this is going to be very exaggerated, so don't get too worried about the beam bending quite the way I'm going to show it here. Let's see if I can make this work. I don't know if I'll be able to do this very well or not, but let's draw that, and then let's make another one. Something like that. And then let's erase the top half of this thing. So these are, they should be actually circles. I drew them more as ovals, but that's going to be okay for our point, for what we're going to do with it. So here's our let's just take a little piece, a little sector of it. Very exaggerated beam section, and let's put some ends on it. And we're not so much worried right now about the shear and bending that are in this beam. I'm more worried about the geometry of this beam right now, and we're going to get to the shear and bending part of it in a second, but this is just worrying with the actual geometry. So let's do this. So something like that. There we go. Those links that I just drew kind of point to the center point of this radius. So again, I drew them kind of ovalish, and then I erased the oval part. But think of these as sectors of a circle, so a perfect circle actually. And this line here, well actually let's measure all the way to the neutral axis. So let's put a neutral axis in here somewhere, kind of through the middle. And from here to here, this distance, we're going to call that R. And R is called the radius of curvature. And that kind of makes sense. It's a radius, and we're talking about a curved beam in this case. So it's the radius of curvature. Now, curvature, not radius of curvature, but curvature is equal to it's actually equal to something like kind of kappa or something. We're going to define it as 1 over r, the radius of curvature. So that's useful to us in a second, because there's a mathematical equation that we're not going to derive, but we're going to write down, that says if you have 1 over r, where r is the radius of curvature, then that equals second order derivative of y over x over 1 plus first order derivative squared to the 2/3, oh no, wait, 3/2 power, I believe it is. So that looks like something we don't really want to deal with. The good thing is that we don't have to deal with this very much. We have to deal with a piece of it, but it's not as bad as it looks. So we do have to remember that we're actually talking about a beam curving, and for the most part, the beams that you build into machines and buildings and things like that, they don't really bend that much. They do bend, but it's very small amounts, not anywhere near what I drew. And so if that's true, if the amount of bending is small, then this dy over dx, that's the slope. So in our picture, it would be right here. Let me scoot our picture up some right here. This guy, the slope of that equals dy over dx. So if this beam really isn't bending that much, that's a very small number. So dy dx equals, or well, is approximately very small in beams. So, you know, they're pretty much flat, but they do deflect some amount, but it's a small amount compared to the size of the beam. So if that's true, I take a small slope. That slope is going to be squared, so it's a small slope that's squared, so it gets even smaller. So this is a radians type thing. If we were thinking of the angle that I just drew, like this angle right here, in radians, it's really small. We square that, it gets even smaller. We add 1 to it, so we add 1 to a really small number, so that's essentially 1. Then we raise 1 plus this really tiny decimal to the 3/2 power, so it just even gets closer to 1. So as long as we're dealing with beams where the deflection is pretty small, which is the way we want beams to behave when we're using them in a design, then this entire denominator is just 1. And so that means we can write 1 over r is pretty much equal to just this part. All of that over 1. And that's not so bad. So now we've got this second order derivative thing. We can probably deal with that a lot easier than what we had before with the actual equation for 1 over r. All right, so we'll hold on to that piece of information. That's going to be important or useful later on, because we have a mathematical way to describe this radius of curvature, or at least the reciprocal of the radius of curvature. All right, let's go back to our picture, our curved beam picture. This blue line that I drew, the dotted one, is the neutral axis. Remember, the neutral axis doesn't change in length. It's the point in the beam that's bending, where it's the actual original length of the beam. Above the neutral axis for this one, a similar line drawn down the length of the beam would get shorter. Below it, it would get longer, because it's in tension below and compression above for the way this beam is bending. So let's do that. Let's draw one here. This red line, red dotted line, is going to be longer than the original one, the blue line, the neutral axis. Let's add another variable here. Let's say that this angle is theta, not the same theta that I drew over here. Maybe I should change this, I wrote a theta over here for that slope. Let's change that to an alpha or something. just so we don't get them confused. This is a different value. It's not the same thing. This is just where we decided to cut the little beam apart. And this is the arc, the amount of radians that this arc sweeps through. All right. So now let's say that the length of the neutral axis, so the dotted blue line, that one, that equals r, so the radius of curvature r, times theta. R theta is just an arc length. So that's just an arc length. The length of this red line doesn't matter anything at all. It's just a line other than the neutral axis. In this case, it's one that is longer than the neutral axis, but we could have drawn a red line above the neutral axis. It doesn't matter. This one is, we need a new variable. Let's put in this y. So remember when we do sigma equals my over I, y is the distance from the neutral axis to the point of interest. That's the same idea here. So it's measured from the neutral axis to some other point, and I've just kind of got it as a random point right now. So the length of this line would be r plus y times theta. Also an arc length. I said line, but it's really an arc length. So that's the arc length of the dotted red line. So now I've got, these are both, when the beam wasn't bent, so when it was here, both of these lines would have been, like there's a neutral axis, there's our red line. They could have gone all the way down the length of the beam. They should be straight. I kind of drew my red one a little crooked, but that's okay. They were the same length. But now that it is deflected, it's curved, the red one is longer than the blue one. And when we have lines that change in length, or dimensions that change in length, we used a term way back like the first week or second week of when we started all of this, called strain. And so we can calculate strain as the change in length divided by the original length. Okay, so the change in length, based on what I've got here, would just be the length of the red line minus the length of the blue line. So r plus y times theta minus r, we'll put that in parentheses just to match it up, times theta, divided by the original length, which was the blue line, r theta, r times theta. Okay. It can be simplified a little bit. Let's expand this top part. R theta plus, well, let's do y theta since I have them in that order. Y theta minus r theta over r theta. In my numerator, I have r theta minus r theta. So those subtract each other away. And now I've got a little function for strain. Y, well, and then I've got y theta over r theta. So actually, the thetas will cancel out once I get rid of the r theta minus r theta. And I just end up with y over r. This r is the radius of curvature r. Okay? So now we're getting somewhere, possibly. I did mention our flexural stress equation. Let's put it, I don't want to get it too cluttered, but I think we can put it over here. Negative m times y over I. Now, I want to deal with the maximum, and I don't know if I've written this equation much. But maybe you've seen it in your book, or maybe I have mentioned it once or twice, maybe, I'm not sure. But sigma max equals, let's just not worry with the negative sign, so that it's going to be the largest value of m, whether it's positive or negative. And y is this distance from the neutral axis that I've got it labeled in green right here. If I want to know the largest value, it's either all the way to the top of the beam or the bottom of the beam. In this equation, when I write sigma max and I want to specify the largest one, I just write C. And that C means to take the largest value of y that you can find, the largest absolute value. It doesn't matter if it's negative or positive. And then we'll divide by I, the moment of inertia. Okay. Now I've got another concept from way back at the beginning, and actually from right here. Remember this elastic region, the slope here equals, well, the slope would be sigma over E, but let's not say equals. Let's write it leads us to Hooke's law, which says sigma equals E times epsilon, and the slope is E. This would be like y equals mx plus b, where b is 0. The y-intercept is 0. So if I've got this equation, sigma equals E times epsilon, and I've got sigma and I've got epsilon, I can combine those together using Hooke's law, as long as I stay in the elastic region of this beam material, which is what I want to do. I don't want the beam to go plastic and be permanently deformed out of shape. All right, so I'm going to use Hooke's law. Sigma equals E times epsilon. For sigma, I'm going to put in mc over I equals E. And for epsilon, I'm going to use y over r, except that just like I had the C in sigma max, epsilon max would be C over r. So instead of a y here, I'm going to put that same value of C. So that what that would do is it would move this red line all the way to the bottom of the beam, or maybe all the way to the top, whichever is further away from the neutral axis. Now I've got an equation that's starting to look a little bit interesting. Let's rearrange it a little bit. So this M is the internal bending moment, and we already know that it varies from one end of the beam to the other. We've drawn this Shear bending diagram, and it's not a flat line. It has all this shape to it. We've done the intervals of the beam where we cut up different intervals and looked at the internal bending moment, and it had different equations. So we know that M is a function of X. So actually, why don't we copy this so we don't get confused that that's what we're talking about. Let's that right. Well, I don't have enough room for it. Let's erase this one. We'll start over. All right. So we know that M. Whoops, I need a pen, don't I? M is a function of X. We see that we have C in the numerator on the left-hand side of the equal sign, and C in the numerator on the right-hand equal side of the equal sign. So those we can divide through by C and they disappear. Let's move E over to the left-hand side. So we have I down here and E. I want those two together because they're both constant. E is a material property that shouldn't change from the beam. Wow, that's loud. And I is the cross-sectional area property, moment of inertia, and that shouldn't change throughout the beam. So I'm going to keep them together as constants. And that leaves me with 1 over r, which is what we started out with over here, making the approximation that 1 over r is the second order derivative of y with respect to x. So now I've got second order derivative y with respect to x equals m as a function of x over, a lot of times it's ei, doesn't matter which order you put them in, but they're alphabetized now. And now I've got an equation that will eventually, once I solve the equation, get me to y over x, which is an equation for the slope, which would be the equation of the elastic curve of the beam. So, the equation of the slope would be the equation of the slope, but if I integrate the slope, that would be the equation of the elastic curve of the beam, because the slope would just be dy dx. So basically, I need to integrate this equation 2 times. One time to get dy over dx, which is the slope, and I have an equation for that. Integrate that equation, and I would get y as a function of x, which is the equation of the elastic curve. So way back up here, the equation of the elastic curve would end up being y as a function of x. So let's see if we can do that. Let's do a relatively straightforward one. We don't need a really complicated set of equations or beam configurations to deal with. Let's do a cantilever beam with a point load on the end of it. So here's our cantilever. Let's put a point load on the end of it. Let's actually cantilever this thing. Let's put some dimensions for the length. We'll just call that L. We'll call the force P. A lot of times our charts are going to use P for the force. Let's set up X. Let's set up our X equals 0 over here and go that way. We're just going to do that to have some of our numbers come out a little bit better. Plus, we don't have to deal with the reactions at the wall since we're using the free end of the beam. It all still works if we do all of those things, just we'd have to deal with figuring out the reaction at the wall, and we don't have to do that, so we're not going to. So this beam has one interval. From x equals L to x equals 0 is the interval of the beam. So obviously you're going to have beams that have way more than one point load on them. Then you'll have to deal with several intervals if you wanted to find the equation of the elastic curve. But for now, let's just figure out how to do it in a simple case. And then we'll actually show how to use some pre-solved equations to combine them together. So let's just cut this guy open randomly in the center of the beam and see what we've got there. So remember, when you cut open the right-hand side of a beam, that you've got the shear force. Could be a function of x. In this case, it's really just a p, but it's a constant, but that's not the point. We've got that internal bending moment, m of x. That's the one that will be integrating over, right? Or integrating in our integral here in a second. Okay, and we've got, in this case, P, the point load. So if we had a different kind of beam, or if we were using the left-hand side, then we'd have to know the reactions and all that. That's kind of the reason I chose a cantilever for this, is because there are no reactions on this side of the beam free body diagram. We just have the internal shear and bending moments. All right, so let's write, just so we can be thorough, let's write a summation of moments about the cut of our free body diagram. we'll do clockwise positive. They have to equal 0 or else this beam is rotating about the cut. This little free body diagram piece is, and we know it's not doing that. It might be bending or flexing, deflecting, but it's not rotating. It's not, spinning. So I've got V of x does not create a moment about the cut surface. I've got M of x drawn clockwise, so that's just M of x. And I've got P times, and now remember I set up where this direction is x. So x equals 0 back here. So when I write my moment for P, it would be clockwise, so plus P times x. And to get an equation for M of x equals negative P times x. So it's really easy equation to deal with, but you could imagine doing this and finding some other equation for M of x. So this is about as simple, other than some kind of constant where it's not doing anything. This is about as simple as you can get for M of x. All right, let's go up here and let's borrow this equation. And start working on it. So we've got second order derivative. M of x is now negative P times x over E times I. So to solve this equation, what I want to do is I'm going to have to integrate it. Integrate the left-hand side and the right-hand side. So with respect to x, let's see if I'll have to move this over a little bit to put in the dx part. And the left-hand side, the integral of the second order just becomes the first order. So I just get dy dx. So that is the slope. So that's technically way back up here, this slope right here, the slope of the tangent line at any point in the beam. So the right-hand side, I get negative 1 over EI is just, all that's constant. And then I integrate P times x dx. All right? So the integral of px dx is px squared over 2, and you generate a constant of integration. So dy over dx equals, let's combine, let's put the p over here. So negative p, and then it's going to be x squared over 2ei plus some constant. I'm going to do c1 because I need to integrate again, so I'll generate another constant of integration in a second. So we'll just do it this way. Let's see. I think I want to rename dy dx. So that's theta of x. So dy dx equals theta, the slope. Let's move the ei over, so we can put ei here. So I just moved them, multiplied both sides by ei, basically. And then I'm left with negative p x squared over 2 plus c1. I suppose I could move the 2 over as well if I wanted to, but I'm going to leave it there. So now I need to find a value for c1. So that means I need some kind of boundary condition where I know something to be true. So if I look at my beam here, I know that as far as the slope goes, because that's what I'm working on right now, that x equals L, so that's back here. If I were to draw the slope of this beam, it's going to do something like this. And I know that at the wall, slope equals 0. It's horizontal where it's attached to the wall. So I can use that as a boundary condition. At x equals L, theta of x equals 0. Or theta L equals 0. So that whole left-hand side becomes 0. And then I'm left with 0 equals negative p, and now x is L, so this is L squared over, we'll leave that 2 in there, I didn't move it, plus C1. And therefore, C1 equals PL squared over 2. So we have a value for C1. Okay, let's grab this equation here and put it down here. Actually, that's not really the one I need, is it? And it's not one, because I have a value for C1 now. So let's plug in these right there. Ah, too far. There we go. So EI theta x, which is dy over dx. So let's do that. EI theta is dy over dx equals, let's leave some room this time, negative px squared over 2 plus c1, which is pl squared over 2. And now if I integrate both of these sides, so integrate this side dx, integrate this side with these guys to combine together, dx. And the left-hand side now is just EI, or constant, so we'll take those out. That leaves us with the integral of dy over dx with respect to dx, or with respect to x, is just y of x. That y of x is the equation of the elastic curve. So we're really close to getting our actual equation now. On this piece, the integral of this guy that's a negative. It kind of got cluttered up in there, didn't it? There's a negative px. So we can do it in parts. Px, negative px squared over 2, integral of that is negative px cubed over 6 plus PL squared over 2. There's no x's in there at all. That's all a constant. So it's just PL squared x over 2 plus my second constant of integration. All right. So going back to here, I also know that at x equals L, the deflection is equal to 0. So not only is the slope equal to 0 at the wall, but the deflection is equal to 0 at the wall. It's not moving up and down where it's bolted to the wall. Okay, so I can take and use at x equals L, y of x equals 0. So the whole left-hand side becomes 0 again. Equals, and now I've got to put L's in for everywhere there's an x. So negative p L cubed over 6 plus p, that's L cubed also, over 2 plus C2. So therefore C2 equals, and I have to combine these things together, I have PL, negative PL cubed over 6, and this would be 3PL cubed over 6 to make it common denominator. So that would give me negative PL cubed over 3 if I add them, well, subtract them and simplify. Right? So you could do that little bit of math if you wanted to. Now, let's plug this thing together. E I times y of x equals negative p x cubed over 6 plus p l squared x over 2 plus, well, minus p l cubed over 3. Okay, let's isolate y of x. We want that by itself. So y of x is the equation of the elastic curve. Okay. We need to collect these with a common denominator of 6. So negative p x cubed over 6 plus 3pl squared x over 6 minus 2pl cubed over 6. All of them will have p in there, so we can take that out. All of them, I just moved the e and I back because I want the y of x by itself, so all of them will have e I together. The common denominator will be 6, and then we would have, if negative x cubed here, we would have 3l squared here plus 3l squared, and then here we would have minus 2l cubed. I guess we could make our EI over 6 kind of centered there, huh? Like that. And now we've got this guy that will model, if we put this equation in MathCAD and plotted it, we would get the exact shape of our beam, our cantilever beam with the point load on the end of it. That's what we would get, is a plot of that beam bending. Now, that's a lot of work to do for a very simple loading situation. Sometimes it is the best way to do. Maybe you do want to plot the thing. Maybe you've got, if you were doing this without talking through every step, it's not that big a deal to do. You put it in MathCAD and integrate your equation twice, and you've got your answer. Particularly if you use definite integrals here instead of the indefinite ones that have my constants in it. So it's not that big a deal to do until the beam starts to get lots of intervals where you have to do it piecewise to put all the intervals together. So this is a very simple case that has already been done. We've got, if we look in our charts over here, I don't think I have one. You could look them up online. I can't right now. But at least in our exam references, one of them is going to have, right here. Let's rotate this guy around. This chart like this. These charts are all over. It's easy to find them. And in fact, there is a cantilever beam with a point load on the end of it. And there's another form of the equation of the elastic curve. They've got it simplified a little bit. They've got px squared 3l minus x over 6ei. Ours is a little bit different form than that. You can see some of the similarities that are between our two different equations here, but they have it simplified differently than we do. But that's okay. They've also got a couple of other things in here. They've got the slope at the end of the beam already solved. So we did generate an equation for the slope right here. We have an equation for the slope, but a lot of times you don't want the slope just anywhere. You want the slope that's at the end of the beam, particularly for a cantilever beam, because that's where it's going to be most deformed. And so they've already solved for that. And they've done that for all these. There are 8 different setups here, at least in this chart, 4 cantilevers and 4 simply supported beams. When we do this again on Monday, we'll start with this chart. So we'll start with how do we use all of these individual cases to build up a more complex scenario. So maximum deflection, they have different equations already built for the maximum deflection. Let's zoom in on some so you can see them a little better. There we go. Yeah, that's on your screen. So it's a little blurry, but you can look one of these up online, and there are plenty of beam deflection charts or tables online that you can look at. So negative PL cubed over 3EI. They have it negative because their deflection is positive when it goes up. So these are all negative because most all of these are causing the beam to bend downwards. It tells you the location of the thing. Let's look at the cases really quickly so we can kind of get an idea of what's already been done. So here we have a cantilever with a point load on the very end. Case 2 is a cantilever, and this is representing a distributed load all the way across the beam. Case 3, we haven't really done a lot of these, but this is a cantilever, and it's got an unevenly distributed load. So this one's evenly distributed. This one's unevenly distributed, a triangle. Here's one cantilever with a concentrated moment on the end of it. This one's actually bending the beam upwards the way they've got the moment drawn. These two look similar. These are both not cantilever. These are both simply supported beams, 5 and 6. The difference is 5 has a point load not in the center of the span. 6, the point load is in the center of the span. So there's a couple of things about 5 that we do have to be careful of. And those have to do with this A and B dimension. So A and B are not the left and right dimensions. A, in fact, it says right here, B must be less than A. So this particular setup, these equations are looking at the beam from the side where the point load is closer to the right-hand side of the beam. So you might be dealing with the mirror image of what your situation actually looks like. So you do have to be careful that the B dimension is the smaller of the A and B. So P, the point load, is closer to the side with the B dimension. Whether that's left or right doesn't matter. It's the smaller dimension. But that does do a couple of things, like this equation here is only going to give you a value between 0 and A. So it's only, the equation of elastic curve is only for the larger dimension. They don't actually have a equation of the elastic curve for the shorter dimension here. They give you a couple of things here, 2 different Y maxes. One is the actual Y max, and the other one is the deflection at the center, but it's not the maximum deflection. So sometimes you want to know at the center of the beam. They're just pointing out that here it is, but it's not the maximum deflection for that beam. This one's a lot more straightforward. It's just point load in the center of the span, distributed load, evenly distributed load all the way across the beam, and then a concentrated moment applied to one end of the beam. Notice on this one that theta 1 and theta 2 are not the same value. So the theta 2, where the moment is applied, is a larger slope than theta 1, the other end of the beam. Same thing here where they give you the maximum deflection and the center of the span deflection. They're not the same. This equation of elastic curve, all of the equations except for this one work for the entire length of the beam. Technically, this one is only half the beam, but that's the beam where it's symmetric. So if you know the left-hand side's deflection, you also know the right-hand side's deflection. They're symmetric to each other. And the slopes are the same, just one's positive and one's negative, but based on where they're measured from. All right. I think that will be enough for the first intro to beam deflection. After this, what we'll do is actually go through these charts and we will go in and use these charts. You can use the charts just as they are. If you happen to have a beam that's exactly one of these scenarios, then you can just use the chart as it is. A lot of times we're going to need to combine these together though. And so that's going to be a process called superposition, basically where you take the individual effects of, say, case 1 and case 2, combine them together to get the combined result. Or you superimpose the two individual cases to get a final result. So we'll do that kind of thing on Monday, and I think that's probably good for today. All right, I will see you guys on Monday, and let me know if you have any questions about this. There's not really any homework associated with just the integration side of this. I'm definitely not going to have you integrate a beam on exam 2, so you don't have to worry with doing that. It is good to know. It's good to see where this stuff is coming from, instead of just knowing that, hey, it exists in a chart. It's nice to know that these equations don't just pop out of nowhere. They have an actual background on where they came from. All right, I will see y'all on Monday, and we will get to work on some calculations for beam deflection.